Okay, so I guess we'll get started. It's a really great pleasure to have Eugen Hellmann here from the University of Münster in Germany. A brief introduction to Eugen. He did his PhD in Bonn, and I guess he graduated in 2011. He was a student of Rappaport, and he was assistant in Bonn for 5 years before moving to Münster in 2016. And he'll be talking about the derived category of the Iwahori-Hecke algebra. So thank you, Eugen.
Yeah, thanks a lot for the invitation. It's a great pleasure to give this talk and to at least somehow be in Australia for the first time. So maybe at some point also in person. I want to speak, well, on the derived category of the Iwahori-Hecke algebra. And what this is actually supposed to be about is trying to upgrade the local Langlands correspondence, or at least part of it, to a statement about categories. Which somehow should fit in the framework of what is nowadays called the geometric Langlands program. So that's roughly what this is about. And so let me kind of explain what it actually is. So in order to do so, I want to briefly recall what the local Langlands correspondence is supposed to be, respectively what its easiest special case is, which is kind of about the classification of modules over the Iwahori-Hecke algebra. So let me fix notations and let F be a finite extension of QP. The p-adic numbers or of Laurent series field in characteristic P. I will denote by small k its residue field. And throughout the talk, I will need this number Q, which is the number of elements of the residue fields. Then there will be a lot of representations coming up, and I want to have a field of coefficients. So all the representations I will consider are with coefficients in C, an algebraically closed field of characteristic 0. And I want to fix a square root of Q in my field C. I'm not sure whether I will actually ever write out explicitly where this choice comes in, but kind of this is one choice that one usually has to make. And then I want to recall what the local Langlands correspondence does. So what it's supposed to be about, it's about to parameterize representations. So on the one hand side, you have the irreducible smooth representations, say pi, of the group GLN of F on C vector spaces. And they are supposed to be in bijection with what is called n-dimensional Frobenius semi-simple so-called Weil-Delin representations. And I'm going to explain what this is. Say rho comma n, also on C vector spaces. And of course, both sides should be taken up to equivalence. So what are these players here? So, supposed to be large. So I want to assume that it's more or less familiar what smooth representations of a group such as GLNF are. So these are representations on C vector spaces where each vector has open stabilizers, so they're kind of continuous for the natural locally profinite topology on GLNF and for the discrete topology on C. So I rather explain what these Berlin representations are. So they are almost something like Galois representations. So we start with the Galois group of F, which has as a quotient the Galois group of its residue field, which is known to be isomorphic to the profinite completion of the integers, which contains the integers itself. And you can take the pre-image and you get a group WF, which is usually called the Weyl group. That was small again. And which then contains the pre-image of 0, so the kernel of this surjection here, which is then usually called the inertia group. Okay, so you have these groups related to Galois groups, and Weyl-Deligne representation consists of a representation rho of this Weyl group, say to GLN-C, such that rho, when restricted to this, this subgroup, factors through a finite quotient. So this is a profinite group, and in some sense one that this action of the profinite group actually comes from a finite group. So this factors through finite quotients together with a nilpotent operator, say n, from C to the n to C to the n. Well, it's an endomorphism which automatically is forced to be nilpotent by the condition that Q to the absolute value of some element of the Weyl group times rho composed with n is the same thing as n composed with rho, where this absolute value is precisely the map up here. So you enforce an equation like this, and this in fact automatically forces n to be a nilpotent element. So these are the Weyl-Deligne representations that showed up here, which are actually quite close to Galois representations. And then there is this condition of being Frobenius semi-simple, which actually rather is a technical condition, but to have a correct statement, let me define it. So Frobenius semi-simple just means that the representation rho is semi-simple. So it's just a condition on rho and no condition on n. Okay, so that's kind of the general story, but maybe more familiar is the easiest special case. Okay, so what is the easiest special case? I just restrict attention to representations pi, which have a non-trivial fixed vector under the Iwahori subgroup. Okay, so it's just a subset, so just supposed to be a subset of the representations here. Okay, and which subset is it? So I is the subgroup in GLN of OF, so where first of all you force all entries to be integers, and then moreover you ask that if you reduce to the residue field, then you become an upper triangular matrix. Okay, so all your entries below the diagonal are divisible by pi, where pi is a uniformizer. And that's the Iwahori subgroup. Okay, and it is maybe well known that the representations which are generated by the Iwahori fixed vector in fact can be described as modules over the so-called Iwahori-Hecke algebra. So this set of irreducible representations is the same thing as the set of simple modules over Hg, both may be taken up to isomorphism, where Hg is the Iwahori-Hecke algebra. And in my notations, it's kind of to really define what it is. It's the endomorphism wing of the compact induction of the trivial representation from the Iwahori to all of G. So you have this huge representation, which comes by induction from I. You take its endomorphism wing, and you get an algebra. And the simple modules over this algebra are actually in bijection with the irreducible representations, which have a non-zero fixed vector under I. Okay. So I said that I wanted to talk about this easiest special case of the local Langlands correspondence. So this guy here should be in bijection with something, namely this should be in bijection, well, to some rho comma n, which are Weil-Deligne representations. And in the definition of Weil-Deligne representation, I asked that the restriction of rho to the subgroup IF factors through a finite quotient. And the easiest special case, of course, is where this restriction is trivial. And if this restriction is trivial, then according to the definition of the Weil group, in some sense, you just end up with the representation of the integers, which of course is just given by one element. So you end up with the parametrization of simple Hecke modules, which might be familiar. So you end up with phi n, and these are in GLN C times, and then maybe the Lie algebra of GLN, where phi is, whoa, what's that? Phi is semi-simple. And n and phi satisfy this equation, n phi being q phi n. Okay, and these may be then taken up to conjugation. Okay, so this is kind of the easiest special case of this local Langlands correspondence. And let me formulate the main aim for my talk, is that I want to lift this bijection to a fully faithful embedding.
Excuse me?
Yes.
You also need n to be nilpotent, right?
Sorry, I just didn't hear it.
So does n need to be nilpotent?
Here n needs to be nilpotent, yes, but in fact this equation automatically implies that n is nilpotent.
Thanks.
So because of this equation, kind of n has to shift the generalized eigenspace for some eigenvalue to the generalized eigenspace with eigenvalue q times the same thing, and there are only finitely many of these eigenspaces, and hence n has to be nilpotent.
Thanks.
Okay, and I want to lift this bijection to a fully faithful embedding of categories, and actually this will have to take place on the level of derived categories. Okay, so that's the general aim for the talk. But before getting there, let me make a remark that first of all, I was just considering GLN, but more generally, I could consider a split reductive group. And then maybe G, the f-valued points of boldface G. And then still you have something like HG, an Iwahori-Hecke algebra. For some choice of an Iwahori subgroup. I in G, so then it's defined precisely in the same terms as above, as the endomorphism ring of a compactly induced representation. Yeah, so compactly induced of the trivial representations. And then very similar to above, you want to parameterize the isomorphism classes of simple modules over the Hecke algebra using pairs phi comma n. So here you start with phi comma n, and where are these guys living now? They are living in a group G check times its Lie algebra, where G check over C is the so-called dual group of G. So G is a split reductive group, so hence it's classified by a root datum. So you can take the dual root datum, view it as a root datum over the field C, and use it to define another group which is called G check. And then you again ask that kind of, well, phi acts on n via the adjoint representation, and just shifts it to q to the minus 1 of n. And you again take these up to isomorphism, and maybe here you want a semi-simple element. Okay, so you again want to parameterize your simple HG modules by this, but you only end up with a map which is surjective with finite fibers. Sorry, I work larger. In fact, you know that the fiber over a point phi n, in fact, is related to the set of irreducible representations of the centralizer of the pair phi comma n. Okay, and so maybe I don't want to give the precise meaning of this. So in general, this map will just only be in injection, and in particular, you have to take well, certain irreducible representations coming up here. So I don't want to go into the details of this, but I just want to stress that there is a parametrization of the fibers and hence of all simple modules of the Hecke algebra, just in terms of these guys, but that this internal representation will depend on additional choices. So this map, the other one not, on an additional choice. Which is called a Whittaker datum. And this will be a choice which in some sense later will come up in my construction, and hence I want to kind of stress that in the parametrization of irreducible representation, it actually occurs. It also occurs for GLN, but only very implicitly, because in the case of GLN, this choice is actually unique. You don't have any choice. Okay, but for more general groups, it in fact does play a role. Okay, so let me go back to GLN. And recall how this correspondence is built. Okay, so the correspondence is built using parabolic induction. Okay, and in fact, this is done in 2 steps. So you first assume that phi n is a very simple building block that I maybe want to call SP of lambda comma n, which means that phi is just the diagonal matrix with eigenvalues lambda q to the -1 lambda up to q to the -n-1 times lambda, and n is kind of a maximal nilpotent element. Okay, so in this case you define the local Langlands correspondence of phi and n to be the generalized Steinbach representation. Okay, and what is this? This is the unique irreducible quotient of a certain induced representation, iota bg, and then you take the unramified character corresponding to the element lambda of C, and tensorize with the unramified representation corresponding to q to the -1 times lambda, and then up to the unramified representation of q to the, well, I guess q to the -n-1 times lambda. So this is an unramified representation of T, which is the diagonal torus, which sits in B, which for me is the upper triangular Borel. And this here is just normalized parabolic induction. So before you induce, you first twist with this so-called modulus character, which is just a nice normalization. Okay, so that's the first building block. But in general, of course, phi and n are not only of these very nice shape, but at least as long as phi is semi-simple, which we always assume here, we can always write it as a direct sum of representations like this. right? Just by looking at the Jordan blocks for the nilpotent endomorphism n, and then you define the Langlands correspondence as follows. You take again a unique irreducible quotient of a representation that will also occur quite frequently in the follows, which is called the modified local Langlands correspondence. And again, this is an induced representation. Namely, for each of these lambda I, Ri, you have the corresponding generalized Steinbach representations. This one, which you can view as a representation of the block diagonal matrices and then induce them further. Okay, so here it's right. Okay, and this here is called the modified Langlands correspondence. And this here certainly in general is not true for any ordering, but for a particular choice for the correct ordering of the eigenvalues lambda 1 up to lambda s. So basically you have to ensure that if lambda j is q to the something times lambda I, then kind of the q to the something times lambda I occurs before the lambda I. Okay, but there's just a combinatorial recipe which tells you which order you have to choose, which comes up when you kind of analyze these parabolically induced representations. So which is called the Bernstein-Seliwinski classification of smooth representations. All right, so this is the classical story, kind of in the case of GLN, in the case of the easiest possible building blocks, the case of representations with a non-trivial Iwahori fixed vector. And so I said that I want to kind of consider a version involving categories rather than just kind of isomorphism classes of irreducible objects. Okay, so kind of to a functor. So then first of all, you need some categories involved, okay? So let's say here we have the category of smooth representations. Of G, and say, if you want, then G is still my group GLNF. It also could be just the F-valued point of some split reductive group. And this contains as a subcategory web IG, the category of representations which are generated as the G representation by the subvector space of fixed vectors under the Iwahori subgroup. Okay, and this inclusion here is actually a direct factor of this category, or what in this theory you would call a Bernstein block. So this category has a block decomposition. It's a product of certain abelian subcategories, and this is just one of them. Right. And this category here, again, in fact, is just equivalent to the category of modules over the Iwahori-Hecke algebra. And then I said I will become derived. So I will consider this category, which then is certainly this equivalent to this derived category of modules over the Iwahori-Hecke algebra. So these are the bounded below derived categories. All right. So these are the categories on the representation theoretic side. So on the side of phi n modules, I will consider the following. So let X G check. So I had G check over C this dual group, which if I consider here the case of GLN, is just the algebraic group GLN over the field C. And so I want to consider all pairs phi comma n in G check times its Lie algebra, such that the defining equation from above holds. So phi acts on n via the adjoint representation by multiplying it with q to the minus 1. Okay, and this is a nice closed subvariety or subscheme of G check times its Lie algebra. Okay, so this is a finite type scheme, which comes equipped with the action of G check by conjugation on G check and via the adjoint representation on the Lie algebra, which certainly does preserve this this equation. And then I will look at the category of quasi-coherent sheaves on G check. So this is supposed to be the category of, well, in fact, I will need this G check action. So it's the category of G check equivariant quasi-coherent sheaves on my scheme X G check. So quasi-coherent sheaves that are equipped with an additional action of G check. And then I can again pass to derived categories. But in this kind of passing to derived categories in this business with an additional action of a group is a little bit tricky. So in fact, the correct object to consider here is the derived or the bounded below derived category of quasi-coherent sheaves on the stack quotient of G check by G of X G check by G check. So if you don't like stack quotient, which kind of pretending that the quotient of this guy by the action of this group would exist. So if you don't like it, then you should just think of this as a corresponding derived category of this abelian category here, which on a technical level is not quite correct, but I mean, kind of the idea of this category is to make this work without too much technical difficulties. Okay, so that's my derived category on the side of phi n modules, and so on the one hand side, I have my representations which was the same thing as the Hecke modules. And this comes equipped with an action of what I want to call ZG, which is the center of web IG. So the center of this category in the sense of it's the endomorphism wing of the identity functor on this category, which you can rephrase much easier for Hecke modules. So it's just the center in the usual sense of the Iwahori-Hecke algebra, which acts on this category. Whereas if you consider these categories of equivariant coherent sheaves, or well, the same applies to this derived category, okay, then you can act on this by the wing of G-check invariant functions on XG-check. Okay, and this just turns out to be the global sections of the adjoint quotient T-check modulo W. Okay, so where T-check in G-check is a dual torus. Okay, so this is just the adjoint quotient. So W is the while group. And so this is just the wing C adjoint X upper star T check, and then the while group invariance, which, if you know the Iwahori-Hecke algebra, indeed is just a description of the center. Okay, so this is the same thing as C adjoint X lower star of the torus T. So this T-check is a dual torus for T, so which by definition just means that these two are the same. And that is maybe familiar description of the center of the Iwahori-Hecke algebra. So you have this the center, the same object acting on both sides. Okay, I continue until I hear protests. Okay, so the main conjecture is that for all triples G, B, and a torus as above. So G is a split reductive group, B would be a Borel, and T a split torus. And again, you in some sense just should think about GLN and kind of block diagonal matrices in GLN as examples. Together with this extra choice of a Whittaker datum, which I want to call psi, there was supposed to exist ZG, so a linear fully faithful functor, which I want to call RG, which well, in fact should depend on psi from the derived category of Hecke modules, respectively, from these representations to this category or derived category of equivariant quasi-coherent sheaves, such that, so if G is equal to T is a torus, okay, which is allowed here, then RT is induced by a very simple thing. So then you're dealing with certain representations of T. So this T naught here is just supposed to be the unique Iwahori subgroup of T, which is just consisting which is just the maximal compact subgroup. So this is just a normal subgroup. The modules over the group ring of the quotient, which fortunately is just the grouping of the co-characters, which is the grouping of the characters of the dual torus, which is the same thing as the quasi-coherent sheaves on the dual torus. But if you look at the defining equation of the space of phi n modules, then you see that in the case of a torus, this is just the same thing as the torus itself. So these categories are canonically equivalent or identified. And then you equip this with a trivial t-check action and push it to the level of derived categories, and you end up here. So it's actually a very simple thing. Okay, and then the whole Langlands correspondence was kind of built using parabolic induction. So my set of functors for all reductive groups should satisfy some compatibility with parabolic induction. So for some parabolic subgroup of G containing my Borel, for a parabolic like this, with Levy quotient phi m, I want that, well, you can do two things. You can first induce and then apply the functor that I would like, or that I conjecture to exist. Or you could first imply this functor on the Levy subgroup, and then you have to do something else. But there's a canonical way to proceed in some sense. Namely, you take some push-pull construction to get from the Levy to the group. And so what are the players here? So this is the normalized induction for the opposite, for some technical reasons, parabolic. And what are alpha and beta? So alpha p is just the map from, I introduced the stack of, the space of phi n modules up here. Well, for the group G check, which maybe was GLN, but I guess you see that you easily can write down the very same definition for any group. So in particular, you can do it for the parabolic and the Levy as well. And that's what I mean by xp check. And then again, you divide out by the action of p check. And then you have a map to the same thing for the Levy. And this is certainly just induced by the fact that you have a map from the parabolic to the Levy, the canonical projection, which induces something on phi n modules. And you have a map beta, which again goes from this guy. And now you go to the group G itself, and this is certainly just induced by the inclusion. Okay, so you take this RM and you end up with sheaves here. So you pull them back here, and then you push them forward, and you end up with sheaves on this XG check. And you're supposed to see the same thing as first inducing a representation and then applying this expected functor RG. And of course, I should say that if you ask these natural isomorphism to exist, then in some sense, the various natural isomorphism like this should be compatible. Okay, so this is, let's see whether I can, so this is the main conjecture I want to state and I want to make.
So I thought that in this particular case, D of like D plus of Q of equivariant coherent sheaves would be exactly the same thing as D plus of coherent sheaves on that stack quotient.
Okay, I'm not 100% sure whether, so it might be true that kind of for GLN or for a reductive group, it even could be the case. But anyway, later I will need this, this thing for parabolic subgroups. And then I'm pretty sure it's not the case. Because for parabolic subgroups, these spaces become really, really evil.
I thought the issue was whether you're linear algebraic or not. Like, it wouldn't be true for, like, because if you just take G, like G times X mapping to X is like an acyclic resolution.
What?
In the coherent world. But I've never understood this properly, but.
I don't know. I always thought it was not so clear how to identify this because, well, in some sense, if you write down this rather than the derived category of this, well, if you write down an object in here, you kind of write down, well, you write down something on here and then on G check times this and so on, such that you have, well, compatibilities, but only up to quasi isomorphism, whereas here you obviously ask whether they are compatible up to isomorphism. Right, and I think I never came across a statement that you can upgrade this for an action of a linear algebraic group, which doesn't mean that it's not true. It's just saying that I never came across it.
So in the conjecture, there's no statement in the conjecture about any like essentially surjectivity, right?
Right. So the functor is not supposed to be an equivalence.
Yeah.
I will have to make some remarks about the conjecture anyway, and this would have been the first one.
I have some other questions. So this conjecture is about a functor between the derived categories. So is it possible that for some nice G like GLN, that there might be a conjecture about a functor between the abelian categories?
Unfortunately not, because this functor is so for example, if I mean, I will give a kind of construction of a functor which kind of has these properties, and then the easiest answer to the question, I guess, is that you just can compute that if you start with the trivial representation here, say of GLN or of GLN in degree 0, then the functor will map it to something which sits in degree 1 minus n.
Okay.
So it really shifts homological degrees. Whereas if you start with something irreducible, well, with an irreducible principal series representation, so with a full induced representation, which happens to be irreducible in degree 0 over here.
Can you say
you in fact will end up in degree 0 on the other side. So there's no easy, no really easy explanation of this.
So I am a bit confused about in your previous remark you said a more general version for the local Langlands correspondence for G and G check, and you said that map is surjective with finite fibers. And
this one here, yes, right. Yes.
And what's confusing me a little bit, because so maybe
sorry. This one here is surjective.
Yes, with
okay.
fiber.
But I didn't say that that this one here was surjective.
Yeah.
And so in some sense, because the question just came up and because I wanted to make this remark anyway, but going back to this classification of simple Hecke modules, you roughly should think about this classification, of course, as being part of the functor that I described below. Okay, and so here you should roughly think about it. It's not literally true, but almost in a certain sense. You should pick some element phi n in here. Okay, and then you try to make an equivariant coherent sheaf out of this. Okay, so what do? Well, you can consider its orbit. Okay, the check equivariant thing of course has to sit on all of the orbit, and then you can just take, well, in some sense, the structure sheaf of this orbit, and well, then you have certain ways to make this equivariant. Okay, and the ways to make this an equivariant sheaf is in some sense precisely corresponding to representation of the centralizer. Okay, so in this sense, you kind of see the structures that you started with in the classification upgraded into this thing with equivariant quasi-coherent sheaves. Okay, so that was one remark. And then there are several more remarks to come, and I'll maybe go back to so the first remark is, maybe the important remark that similar conjectures or results have been around in the past years, namely in ongoing work of, on the one hand, David Bensby, then Harrison, Helm, and Nadler. And on the other hand, Xingwen Zhu also is working on these objects, on related objects. Okay, so that other people working as well on the subject. And now let's go back to kind of the mathematics. So why do I consider this to be a functor just between derived categories? Okay, the reason is that you compare in a sloppy sense flat structures with non-flat structures. Okay, so what do I mean by this? For example, if you take the Iwahori-Hecke algebra HG itself, then you maybe know that it's flat over its center. It's even as a module over the center, it's just a finite free module. Okay, so there's not happening much. Whereas on the other hand, if you take this space of phi n modules and you map it to the adjoint quotient, which is how the action of the center comes about on categories of sheaves over this. So I maybe should have introduced this map before, but you just map phi n to phi, and then you map to G mod W, which is mapping phi to the characteristic polynomial. Okay, so that's the map to this adjoint quotient. So this is not flat. Okay, and the easiest way to see this is that if you have a closer look at the geometry of this space here, where you just compute that the irreducible components of xg check in fact are in bijection with the possible Jordan canonical forms of this nilpotent endomorphism N. Okay, so that's something which just comes out of the analysis of the geometry of this. But here you see that if N is not equal to 0, this equality N phi, being Q phi N, of course enforces relations between the eigenvalues of phi. Okay, and so this means if here you are on an irreducible component corresponding to N not being equal to 0, you can't sit over all of this adjoint quotient because, well, you must satisfy some equations. So this map, in fact, kind of contracts certain irreducible components of this guy to something which is, well, kind of properly contained in here. Okay, so hence this map can't be flat. But kind of this, or modules here sitting via this map over the joint quotient corresponds to things over the Hecke algebra sitting over the center, this being flat and this being non-flat, and you want to compare these things, it in some sense doesn't work if you do it on the level of abelian categories. Okay, so that's maybe one of the first hints why you want to do this. And in fact, it's even worse. So I just, in some sense, very sloppily wrote in this conjecture that you want to have a compatibility of the various psi PG. So what do I actually mean by this? I mean by this, if I take two parabolic subgroups, one contained in another, then I can, in some sense, first induce from the smaller one to the bigger one, and then induce to the full group, or I can directly induce from the small one to the full group. Okay, and these are the same thing. But these being the same thing, I force kind of the composition of functors like this again to be of the same shape. Okay. And if you spell out what precisely this means, you see that you run into a problem with kind of base change morphisms between these maps. Okay, and these problems are resolved if you consider the space of phi n modules for a parabolic subgroup not as a scheme but as a derived scheme. Okay, so this forces us to define this x p check, which was in p check times its Lie algebra, not as the zero locus, but to define this as the derived zero locus. Of this set of equation adjoint of phi applied to n is q to the minus 1 times n. Okay, so this is just a set of equation, and what you want to look at is the Koszul complex defined by this equation, which unfortunately for parabolic subgroup turns out to be non-exact, and so you don't just want to remember the kind of ideal, but you want to remember the whole Koszul complex. And this is what's behind this. All right. Then the last remark I wanted to make is that I said that it's supposed to depend on the choice of this Whittaker datum. So what is this Whittaker datum psi? So it's the choice of a generic character, generic really in a technical sense, which maybe I'm not going to define, of n, where n in B is a unipotent radical. Okay, so Whittaker datum is just this choice of a Borel together with a generic character of its unipotent radical. And then one of the nice properties, this functor Rg, which in fact was supposed to depend on psi, is supposed to enjoy, is that if you look at the compact induction of your generic character, well, I maybe have to project it to the block I'm considering. So this is supposed to be the image of this compact induction in the block web IG. Then this is supposed to be the structure sheaf. Okay, and well, that's maybe the easiest thing how you can kind of bring in this choice of a Whittaker datum. All right, so these are the first remarks on the conjecture that I wanted to make. So I maybe should first ask whether there are questions.
Eugen, the derived business always shows up, or is it only for certain parabolics that it's not exact?
All right. So in some sense, this always shows up if your group is big enough. So this thing here is needed for GLN if n is larger or equal to 6, I think.
Mm-hmm.
So for GLN and small n, in some sense, this equation here still yields an exact Koszul complex. So this guy here is a complete intersection inside here. But if n becomes large, this is not true anymore. And the reason is in fact kind of a little bit hidden here. Okay, because what's actually behind this? Behind this classification of the irreducible components is the map of xg check to the nilpotent cone. Okay, you project it to the set of possible n's. Okay, and the set of possible n's, okay, n is nilpotent, so you map to the nilpotent cones. And for a reductive group, the action of the group on its nilpotent cone only has finitely many orbits. Okay, but this behavior fails for general groups. So for parabolic subgroups of a reductive group, it fails. And this here is precisely the bound in GLN where this starts to fail. So for GL2, you easily can convince yourself that it's still, in some sense, just 2 orbits. And then for GL3, 4, 5, it still continues to hold. But for large n, unfortunately, this action is not by finitely many orbits, and then you lose the exactness properties. That's a bit tricky. But well, I mean, there's this derived version which saves the world for us. At some point, I should mention some results, but I also wanted to mention the example of GL2. so maybe I start with the results and construction, and then hope that I will have time for examples. But a talk without results is maybe not the best idea. Okay, so what are results? So if you deal with something about reductive group, then I guess the first thing you should check is whether everything works for GL2, which fortunately is okay. And after that, you maybe should try to deal with GLN. And there, let me give the following formulation of a result. There exists some candidate, let's say, for this functor RG, which you can write. So this is, the functor from the derived category of Hecke modules to the derived category of quasi-coherent sheaves on this equivariant quasi-coherent sheaves, which you can write as the derived tensor product with a certain module that I want to write mg. And okay, I mean, this is not commutative, so there's a slight problem of passing between left and right modules, but on the Iwahori-Hecke algebra, you have this main involution, which identifies the Iwahori-Hecke algebra with its opposite, and hence, in some sense, you can, via this main involution, consider some module here, some left module here as a right module, and kind of do this tensor product. Okay, and so there exists a candidate for such a functor given in explicit terms like this, such that the following things hold true. So RG is, that's something I asked for, is linear for the action of the center. It satisfies compatibility with parabolic induction. Well, at least over a large open subset. The large open subset of what I would call regular elements. It has the last property that I was asking for, namely, if you take this generic character and induce it and apply this functor to it, you see the structure sheaf. Okay, and at least for phi regular semi-simple, so regular here is hopefully not important, but at least for my computations I need it. Then you have these simple modules corresponding to the local Langlands correspondence. Okay, and you want to evaluate this functor on them. And the outcome for these modules is actually maybe not so nice. But if you instead do this modified correspondence, so you take the induced representation of which they come as a quotient, then you actually get something very nice. Namely, you get the structure sheaf of their G orbit, well, which is a locally closed subset. So you close it up, you have a closed subset, which is G-check equivariant, and then you take the structure sheaf of this G-check equivariant subset. So that's all kind of corresponding to the classification of the simple modules here. And then let me put this into quotation marks because I don't want to give the precise formulation. You have some kind of compatibilities with dualities, namely on the side of Hecke modules, you have the Selewinsky involution, and this corresponds to kind of the Serre dual up to a small modification. Okay, and if I put this in the theorem, I should restrict to this regular subset, because I mean, yet I can't really prove everything I would like to be able to prove outside of this regular locus. Okay, but that's already very promising, and in some sense enjoys some very nice features, like via this line. In some sense, you recover the classification of Hecke modules. Okay, so in some sense, it's all about constructing this candidate or this family MG. Okay, so how to construct this MG? Okay, so there are two possibilities in some sense, or two candidates. One is coming from the formulation of the conjecture. Okay, so namely the compatibility with parabolic induction in the conjecture leaves us in some sense just one choice. So this enforces that MG has to be the derived derived direct image of the structure sheaf on the stack for the Borel. Okay, so here beta. Is this projection. Why this? Well, because this MG, if the functor should be given by the tensor product with MG, then as a sheaf on this guy, MG itself must be the image of the Hecke algebra. Okay, of the free module of rank 1. But the free module of rank 1 over the Hecke algebra is induced from the Hecke algebra of the torus. On the torus, we prescribe what has to go on. So if you write out compatibility with parabolic induction, you just end up with this object. Okay, so this is a unique choice that you have. And what's acting on here you of course have the structure sheaf of xg check acting, but you also have acting, because you come from the Borel, here you only also have an action of the Hecke algebra of the torus T, okay, where you use that the Hecke algebra of the torus is just identified with the functions on the dual torus, okay, and so this is kind of the canonical object that you start with, and you have to try to extend to an action of Hg. Okay, so that's one obvious thing that you can try to do, and then see whether this functor, which then somehow by definition satisfies compatibility with parabolic induction, has all the other nice properties that you wanted to enjoy. So the other approach is in some sense where I was rather coming from when I started to consider these objects. Namely, RG is expected to satisfy something like local global compatibility. And I don't want to spell out what all this means. But this, well, rather sloppy statement implies that you have another candidate for MG. Namely, MG should be, well, okay, I consider it as a Hecke module, so these are the Iwahori invariants in a certain representation VG, and this is the family of G representations on my space XG check, or on the stack quotient, which is interpolating with modified local Langlands correspondence that I introduced before. And the existence of such a family and its relation to something called local global compatibility was suggested in work of Emerton and Helm. Okay, and so what is this supposed to mean? So this has two features. First of all, it has again something to do with this generic representation, which is the compact induction of this generic character, and then again you project it maybe down to the Bernstein component we are dealing with. Then this certainly is a module over the center, and the center certainly acts on the structure sheaf. Okay, and so you kind of constantly, in some sense, constantly prolong this representation over here, over your stack, or over your space of phi n modules. And then the representation VG is supposed to be a quotient of this guy, and at least at generic points, and conjecturally everywhere, the fibers of, so you pick a point X, which consists of some phi and n, and then you can take this big family and take the fiber at a point X, okay? And basically this fiber should be the modified local Langlands correspondence for phi and n, up to the fact that first of all, this only makes sense if phi is semi-simple. So maybe you semi-simplify phi. And then there is some nasty issue with duals, namely you rather want this to be the contragradient, and you also have to dualize here. Okay, so this looks maybe a little bit strange, but from the point of view of representation theory, once you ask this condition, well, you have no choice to get around these duals. So what do these duals do? If you take the dual on both sides, in some sense, this says that you take your representation, which is not irreducible, but has some decomposition series, some Eugen Hellmann filtration, and you, in some sense, turn it upside down. So you make the quotient a sub and the sub a quotient and so on. Okay, and if you know this this Langlands classification a little bit, then you know that this modified Langlands correspondence has a property that the true Langlands correspondence is a quotient, but it also has a unique sub-object which is a generic representation. And generic always means that it's a quotient of something like this. Okay, but if this representation here comes as a quotient, then this means that all the quotients of that all simple quotients of this guy here have to be generic. Okay, so in some sense, if you take the fiber, then this must have a generic quotient and not a generic sub. So this maybe explains a little bit why you have to double dualize here. Okay, and the main idea is that I want to use B to extend the HT action in A to an action of the full Hecke algebra. Okay, which means that in some sense I start with this family, which in some sense is already constructed, which is a Hecke module, and I just show that this MG here agrees with this MG, which comes as a direct image as a module over this guy here, but this in additional actually has an action of the full Hecke algebra. Okay, so this is the main strategy, and as I should maybe stop. I should say that with identification, so this means identify well, I called both MG, so maybe I should call it VG and the I invariance with R beta lower star of the structure sheaf. Okay, so as OX G check, what G check tensor Hecke algebra of the torus modules. That's what we want to do, and this works fine over the regular locus. X G check regular consisting of phi and n, which stabilize only finitely many flags. So in particular, if phi is regular semi-simple, you are always in the regular locus. Okay, so that's this here is in fact the definition of the regular locus, and in fact I expect, and this is also what in some sense kind of tells you why you can compute that everything is true in the case of GL2. So we have this open embedding. In here, and the complement has codimension larger or equal to 2. And then the thing in question, namely this R beta lower star of O X B check mod B check. This, well, looks like it it should live in quite a range of cohomological degrees. Okay, but this should be in degree 0. Sit in degree 0, and it should be a maximal Cohen-Macaulay module. Okay, and once you know this, which is, if I computed correctly, then it's okay, at least for GL2 and GL3. And once you know this, in some sense, everything extends from the regular locus. It's the same thing as J lower star of, well, this R beta lower star O X V check mod V check restricted to the regular locus, and the Hecke action extends. Okay, so this is in some sense how you technically start building this, and well, this is kind of how these how you use these two candidates that you have, the one coming from parabolic induction and the other one in some sense from local global compatibility, or from this Emerton-Helm family, in order to construct the candidate for this functor. Okay, and I guess I should stop here. Thanks.
Does your derived category of Iwahori-Hecke have something to do with the derived category of G bundles over the Fock-Fontaine curve?
Yes, it does, and this is one remark I should also have made, because it also answers a question that arose during the break, namely here in this conjecture. I only conjecture this to be a fully faithful functor and not to be an equivalence of categories.
Mm-hmm.
Okay, and in some sense, this failure of being essentially surjective, this is well, if you move, instead of just considering smooth representations, to bundles on the Fock-Fontaine curve, then this issue goes away, and you will have an essentially surjective functor. Oh, will have certainly means something which is highly conjecturally. Okay, so there is you maybe heard or can watch videos of talks of Scholze on the categorical form of Fock's conjecture. So this is due to Fock and Scholze. Okay, so where you have something like the derived category of QL bar sheaves on a certain thing called Bungie. Okay, and this, well, I mean, it's a conjecture, right? So this is supposed to be the derived category, or okay, so what's the formulation? I guess I will run into some difficulties for kind of incompletion. So this is supposed to be the, well, what I guess Gates-Gary would call the category of int-coherent sheaves on the stack of all veiled linear representations. Okay, and I was considering the situation for my thing XG check. okay, which actually lives inside the stack of all well-defined representations. And this inclusion here is in fact the connected component. Okay, so on the other side, you have fully faithful embedding. So kind of on the Galois side, and on the representation theoretic side, there exists the fully faithful embedding, which in fact can realize very geometrically, and hence it has the name J-Lower-Schwieg, from the category of smooth representations of G to, kind of, let's say, the derived category, to the derived category of these QL bar sheaves on bun G. Okay, and so here I was again considering one particular block of, and in some sense you can embed everything into this much larger world where this issue with just being fully faithful and not essentially surjective conjecturally is supposed to go away. And well, in fact, this category, this conjecture about the Iwahori-Hecke algebra, you can extend to a conjecture about the whole category web G, and then here again you have the stack of all value representations. So, which really would be the corresponding fully faithful embedding of this category into this category of incoherent sheaves on the stack of all value representations. But failing to be essentially surjective really has to do with this larger ambient category of sheaves on bun G. And this is kind of in the Fark-Fontaine sense. Okay, so this is a kind of stack of G bundles on the Fark-Fontaine curve. Which is not an algebraic curve. Okay, so this is something really p-adic.
One thing I was wondering is how to see, like on the right-hand side, I can tensor by a G-check module.
On this side?
Yeah, before the fancy version, just in the,
yeah, okay. Maybe in the fancy version, the answer is easier. Where's the conjecture? Here you can tensor by a G-check module.
And right. I'll work out how to do it on the left-hand side.
Well, I mean, it's because here I have not an equivalence, but just a fully faithful embedding. In fact, I really should go down to the fancy version again. Because for the fancy version, you have this operation, which is called, I think Gates theory called the spectral action. But it's not clear whether it kind of preserves this full subcategory here. So okay, to be correct, I should say I guess it's clear whether it does this, but I guess the answer is no. So it does not. I only have to think whether it already happens if you just take G-check representations, but. Oh, okay. In some sense, naive phrasing, this action never can preserve this. Okay, the reason you have to, unfortunately, really stick to the fancy version. The problem is that, okay, this stack here has different connected components. And this stack here has many connected components as well. But it's not that these connected components here would match these connected components. That's not what's happening. And in some sense, what really can happen is that if you stay here on one connected component, but act via representations of your group G check, then here you will move to different connected components. But this embedding is, in some sense, I suggestively wrote this in geometric terms. So really you have the inclusion of the classifying space for this group, but really for this kind of p-adic group into bun G. And you can identify representations with QL bar sheaves on here. So in particular, you see that this would stay inside of one connected component. Okay, it's just kind of the J lower shriek of something. So these sheaves are really just supported on one connected component. And so but the representation kind of will move them. So the quasi explicit form has its defects in some sense. That you don't have all the nice structures that you want, and if you want to have them, you have to stick to the fancy version. But then you also have to stick to a different speaker.
Okay, so thank you very much, Eugen.
Yeah, thank you. It was a pleasure.
Thank you very much.